Okay. Now, of course, as soon as I start recording, it no longer is showing. Take 2, 3, 2, 1. All right, that's good news. Okay. So what I want to do today is talk a little bit about one of my favorite techniques in mathematics. And this can be used to prove a lot of different problems. Some of my small students have used this very productively over the past couple of summers. Some of my thesis students have used it. It's something that doesn't fit into the standard curriculum in most places. The only place I'm really aware where it's done consistently is when I teach a problem solving class here, because this is one of the really good techniques. And so it was really nice that we had a little plug for Math Puzzle Night in the Putnam. This is a wonderful technique for solving some of the problems there. So I'm going to first give an example of monovariants through the famous zombie problem. You could, of course, change this to COVID, but I think we've talked about COVID enough. So for classical purposes, I will go back to zombies. If you've taken a class with me, you've probably seen a variant of this slide numerous times or hear me quote something like this. There's a lot of different ways of phrasing the law of the hammer. I like the last one because it's shorter and concise. If all you have is a hammer, pretty soon every problem looks like a nail. And there's a couple of ways to look at this. One way to look at this is if you are really good at something, whatever anybody asks you to do, you will convert it to what you're good at. If you've ever listened to a presidential debate, doesn't really matter what the question is, 30 seconds into the discussion, the person goes into their fixed spiel of what they want to say. If you have something that you're really good at, whatever I give you to do, try to see, can I work it into a way where I can use my tools and techniques? A better way to view this quote is go to the land of the screwdriver. If they could have solved the problem using their methods, they would have solved it by now. They're smart people. If you have a different perspective, so I've written papers in so many different fields outside of mathematics by applying some insights from number theory and probability in regions where people haven't really looked at the problems that way. And it gives you a really good competitive advantage. This is one of the advantages of being at a liberal arts college, is getting these different perspectives on how to look at things. All right, so I want to just briefly describe the zombie game, and I'll describe the rules. So if you share 2 walls with somebody who's infected, you become infected. And once you are infected forever. So I love to have lots of participation. So if I give you a configuration like this, we'll call the bottom row 1, row 2, row 3, row 4. Who gets infected next? Row 3, we're in row 3. Third one over. Anybody else? Yes. Row 4, which one? Second one. Okay, does anybody get infected again? Yep, so you can see these 2 cells will be infected. Let's come up over here. And it's not hard to see that you'll have another infection. But what's nice now is we have stabilized. And so we do not have a complete zombie apocalypse. It is contained to the upper right corner. And there will be parts of the board that are safe. All right, so there's a lot of questions you can ask. So the first is, what do I need to ensure that at some point in time, the zombies will conquer the entire world? So I want the easiest, most smart alecky, smart ass answer you can give me. What is the simplest board configuration that will guarantee? Yes, right? Look at extreme cases. Don't spend your time trying to come up with some clever thing if something really straightforward works. Infect everybody. Okay, this is expensive. We have to have n squared cells infected initially. Can somebody give me anything a little bit better? Okay, checkerboard. And in fact, the checkerboard is the next thing that I list. There is something between the checkerboard and everybody. What's normally? Yes. Yeah, everybody except 1. So if you do everybody except 1, it's just a little bit better, but it's still of size n squared. I'm glad that you went to the checkerboard though. That's a 50% savings. So now we're only using half as many. And then the question is, how far can you push ideas like this? Anybody want to conjecture the minimum number of infected people we need? And I've actually infected several people right now. Oh, no, sorry, that's probably not funny these days. That's why we have everybody socially distant during these talks. Yes. Okay, why? What configuration are you thinking of? All right, so you're thinking going down the diagonal. So if you take the diagonal and you look and see how it spreads. This is wonderful animation, isn't it? And you can see it just keeps pushing out, pushing out, pushing out, pushing out, and it will infect everybody. Okay, so you've now established an upper bound, that n people will clearly be enough if done intelligently. Do you think we can do n-1 people? And if you've taken the class with me, you are not allowed to answer at the spot. So what do you think? How would you get some intuition as to whether or not you can do it with n-1 people? What would you try to do? Okay. So we can go back to the full diagonal, and then what? So if we go to the full diagonal, you could try to remove just one square and see what happens, and then prove that you'll have two regions. So that tells you that if you take the full diagonal and remove one, it's not going to work. But maybe there's a more clever approach. How would you start to get some feel for what the answer might be? What might you do? So if I give you a hard problem, try to do a smaller, easier, concise, concrete one. What might be a simpler problem to do? So rather than doing the general case of n-1 on an n by n board, what might you start with? 2 by 2. Wow, come on. No, come on. I mean, don't make life easy on me. I mean, I found out, with very little notice I was giving a talk today. So come on, make it a little bit easier for me. What should I? 1 by 1, right? So I start with a 1 by 1 board with nobody infected. Okay, very easy to see what's going on. I could have a 2 by 2 board with only one infection, not going to spread. For the 3 by 3, it's a little bit more interesting. You could say there's 9 places for the first, 8 for the second, which is 72. But since order doesn't matter, there's really only 36 pairs of squares you could infect. Or you could start to use symmetry. If I infect the center as one of my 2 squares, then if I just rotate and and reflect, there's really only 2 possibilities for where the second square is. And for the other 2 configurations, there's only 5. So there's only 12 cases to check. So if we do all of these cases, we haven't proven the general result, but we've built up some intuition that already we see can't do it with just n-1 on boards up to size 3. So how do we generalize this? So the idea is to use something that's called a monovariant. And I'll define this formally a little bit later. A monovariant is a quantity that only moves in one direction. So can somebody give a quantity associated to yourself that you don't mind sharing in public that is a monovariant, that only moves in one direction? I'm sorry? Your age, right? I don't think there's anybody here whose age runs backwards. How about something associated to you that is not a monovariant? Your hunger, right? Hunger, weight, that should probably not be constant throughout the day or moving in just one direction. If it is moving in one direction, we can probably figure out which direction it's going, and it's not going to be good, right? Most quantities in the world will go up and down. It's very rare to have a quantity that moves in only one direction. So an invariant is a quantity that's fixed, that's always constant. A monovariant is a little bit of a weakening. It can only move in one direction. The difficulty for these problems is coming up with what is the right idea to study. It's the aha moment in mathematics. How do they think to look at that? The more problems like this you do, the easier it becomes to see what is the right approach, what is the right quantity to look at. And so here, a terrific quantity to look at is the perimeter of the infection. So I only care about the number of sides on the boundary of my infection. So imagine I have this white cell that is not infected, and it's surrounded by 2 infected cells, so it's going to be infected at the next turn. What I can do is I can look at, of the 4 sides of the cell that's about to become zombified, I think that's the correct word, I can ask how many of those cells were initially part of the boundary and how many of them are now part of the boundary after the infection. Because only its left and right neighbors are infected, 2 of its sides are initially part of the boundary and 2 of its sides are not. After it's infected, the 2 sides that were are now interior sides and they're not part of the perimeter, but the 2 outside sides now are part of the boundary. So the perimeter of the infection is unchanged. Well, I could do, instead of having a cross, I could have 2 next to each other. And again, you can see that the perimeter of the infection doesn't change. Okay, what do I have to look at now? What's the next configuration? I'm sorry? But I'm only focusing just on this square. So this square will be infected, and then later I can come back and look to that. So I'm looking at just this square. What do I look at next? So I've done all the cases where there are exactly 2 neighbors that are infected. So I have to look at 3 neighbors that are infected. And I can always rotate so it looks like this. And so initially I have 3 sides that are part of the perimeter. And after the infection is only 1, so the perimeter has decreased by 2. And the last, of course, is, on every side you see the zombies approaching, it's not good to do you. And 1 moment later you're infected and the perimeter goes down by 4. So the perimeter is a monovariant. So if we have n-1 cells that are initially infected, the maximum possible perimeter of the infection is 4n-4. So why does this mean that not everybody can be infected?
For everybody to be infected, you need 4n.
Good. So for everybody to be infected, we would have to have a perimeter of 4n. So again, monovariant, as time passes, the perimeter of the infection never increases. The perimeter of the full square is 4n, so at least 1 square is safe. And now this is a wonderful example of toehold mathematics, that once you get your foot in the door, you actually get a lot more. So you had initially given me, after infect everybody, you had gone straight to the checkerboard. But I wanted to backtrack and talk about, well, there's actually a little bit of a weaker thing we could say. We could say everybody but 1 is infected. So right now we've proven that at least 1 square is safe. Is it possible that there's only 1 square that's safe? No. What would happen to that square? It would have to be infected. So even though the proof initially only gives you that 1 square is safe, you know that there has to be at least. So a natural conjecture is n. To be perfectly safe, I'll say there has to be at least 2. And then you can think about how can you put those 2. So what do you think you might have? Maybe a whole row or whole column somewhere that's safe. Maybe the region of the infection has to be a union of rectangles. So as a nice problem, try to figure out just how much information do we have now that we know at least 1 square is safe. Do we have to have a whole row or a whole column somewhere? Okay. So I want to turn now to a very interesting application of this. So this is due to John Conway, who was a phenomenal world-class mathematician. He was also extremely generous with his time. I was fortunate to be a graduate student at Princeton during his time there. And he, better than anyone else, knew how to take the most strange statements and find incredibly deep mathematics. We could spend a semester easily giving talk after talk after talk. And in fact, my colleagues at Michigan did this last year during COVID, of just so many of his fun items. So I've just listed a couple of them over here: the game of life, the monster group, audioactive decay, and the 15 and the 290 theorems. One of the nice famous parts about this is the initial proof was actually lost in his office. And it was easier to just reprove it than to find where the papers were. So as a piece of advice, if you ever write down something that you care about, please scan it, take a picture, send it to yourself, file it away. All right, so here's how the game works. So we have an infinite checkerboard. And the rule is pieces can jump either horizontally or vertically. And if you jump over a piece, the piece has to be adjacent to you. And when you jump over the piece you jump over is removed. And the initial piece that's doing the jumping stays in the square where it lands. So over here, you can look at 1, 2, 3. Over here, this piece jumps over this one and now ends up over here. And I have killed this piece which was jumped over. So this shows you that it is possible with the infinite checkerboard to have a sequence of moves where a piece ends up 1 unit above the start. So we will call this row 0, row -1, row -2. We'll call this row 1. So easy proof that you can get a checker piece up at least 1 unit. Can somebody give me a way to get a checkerboard piece up 2 units? Any thoughts as to how you might do that?
The piece jump left into the white space and then jump above the piece.
Okay, so what do I do now?
You take a
a piece and jump right. Okay, good. So I can take this piece, jump over here, and then jump up. It just took me a second because for me, it was natural to go boom, boom, and then boom, which is far more moves, right? So there's multiple ways to do it. So it's not that bad to get something, up to height 2. A huge part of mathematics is then just figuring out what questions to ask. Well, it's natural to ask, can I get a piece up to height 3, up to height 4, up to height 5? If I can give you a constructive series of moves that gets you a piece to height 3 or 4, then it's not hard to prove that I can do it. But what if I'm trying to get something of height 5 and I spend, or have my students spend a couple of hours and we can't find anything? Well, maybe we're not being clever. Maybe it's an extremely complicated move. And how many people have heard of Conway's game of life? So if you've heard of that, there's a lot of very interesting configurations that took people a lot of time to find. To find finite configurations that led to an infinite generation of mass. And so just because you haven't seen anything doesn't mean it can't be done. So we want a powerful tool that will allow us to look at a problem like this, or more importantly, a whole class of problems, and determine when is something possible. And this should be no shock, given that the title is about monovariants, that the idea is to associate a monovariant to this. So the question is, what monovariant? Does anybody have any idea what's going to play a role in the monovariant? So if you read the title, or look at the shirt that I'm wearing, so the golden mean, the Fibonacci numbers, are somehow going to play a role in this. And to me, this is one of the more interesting applications of the Fibonacci numbers. This is not a situation where you would expect the Fibonacci's to be emerging. And so what we want to do is we want to try to figure out what is a good monovariant to put on something like this. And so here's a picture that I stole from the web. And what I like is, things are color coded, although for me, I think I have trouble seeing the difference between the red and the orange when I'm looking at the screen. On my iPad, it's very clear that it's red and orange. And what we're doing is we have some target that is 5 units up. And we might as well assume that the x coordinate of the target is 0. It's at the point 0, 5. And the goal is, can we get a piece that high? And we're going to put a value at every point on the infinite plane. And the value is going to be your distance from the target. And how are we going to measure distance? Does anybody know the name of this? What distance function is this? Yeah, it's a taxi cab metric. You only move east, west, north, south. As a Bostonian, I truly despise New York, but I have to admit Manhattan does one thing better than Boston. The grid system. When you compare that to driving along in Boston, where Beacon and ComApp can actually cross each other multiple times and change which one is on top of the other. It makes it very interesting to get around. Whereas here, it's very clear what's on top, what's on bottom. It's very clear how to move around. So here, anything that's 1 unit from this, I'm going to give an X. Anything that's 2 units, 2 units to the right, 2 units to the left, 1 unit up, 1 unit to the right, 2 units up, it gets an X squared. Another way of saying it is just, it's how many I's left and right and how many J's up and down do I need to get to? And so we put this on everything. What's nice is, as I go down, each row is the previous row, the row above it, times X. So it's very easy to figure out what goes down, because, well, of course, to get from here to T, I just go up 1 and then take that path. So what you can do is you can look at the value of the initial board. And then what you can do is you can look at, imagine you have a piece at the target and a piece nowhere else. That would be the smallest value you can have with a piece at the target. If you can show the value of that is larger than the value of the initial board, then you know it's impossible. Sure. But I missed the punchline, so I was about to do the punchline. So yep, no problem, no problem. The dramatic moment is sadly gone. So if we look at the value of the initial board, and let's say the initial value of the board was 13. And we show if you remove everything from the initial board and have one piece up here and it's 17, then we know it's impossible to get to a piece that high so long as we know that the value of the board is a monovariant and is never increasing. And that's the punchline. So as long as we can show that any move we do does not increase the value of the board, then it's going to be impossible that we could get something 5 units up if that leads to a configuration that has a higher value than the initial configuration. No, I have not. Nope, I have not defined it yet. But what do we think X is going to depend on? What do you think X is going to be a function of? What number? It should be some function of phi. Now, we can't just take X to be the golden mean because we want a finite sum. And if I take the golden mean, well, each row is going to have an infinite sum and I have infinitely many rows. And so that's not going to help. So I need a number related to phi that is finite and is nice. Anybody want to guess? So it should be less than 1 in absolute value. It should be positive. Anybody know a nice number related to phi that's positive, less than 1? Yes? 1 over phi is one of the guesses. Phi minus 1. So 1 over phi and phi minus 1. Are they the same number? Interesting. I once got in the record, they asked a bunch of people in the department, what is your favorite number? And I said the golden mean with a straight face because of its many remarkable properties. Perhaps the most interesting is it's the reciprocal of its own inverse. And it's amazing what you can do if you can keep a straight face. It's, with masks now, it's not a challenge. But so if we take X to be phi minus 1 or 1 over phi, it's less than 1 in absolute value. When we do these sums, these are going to be geometric series. They have a chance of converging. They're getting smaller as we go down. Maybe that's another geometric series. Maybe that's going to give us finite mass. And so again, just doing everything explicitly, we're going to attach the value xi plus j to a point that's I units horizontally and j units vertically from our target. And now let's just figure out what is the sum of the initial board. Well, the 0th row, going back, it's over here, it's x4, here's x5. So x5 is the smallest, and it goes x6, x7, x8 to the right, and then x6, x7, x8 to the left. So the 0th row is going to be the following. And so if I look at the sum, it's just x to the 5th, and then twice the sum of x to the k going from 6 to infinity. Well, the geometric series has many remarkable, wonderful properties. One of them is that if you just truncate, sure. Well, what I've said is I'm going to look at the sum. I'm just calculating the initial value of the board. I haven't shown it's a monovariant yet. What I've said is I hope it's a monovariant. I hope that if we take X to be related to the golden mean, everything's going to work out nicely. But I haven't said right now, I'm just trying to calculate what is the value of the board. Then we'll see that when we do the jumps, the value of the board never increases. Well, right, where your I units to the right, left, and then J units up and down from the target. And that's why when you look at the initial board, over here, this has a value of 1. And then this point over here, it's x to the 4th because it's 3 units to the right and then 1 unit up. So it's 1 over here. If I want to figure out what power of x to put over here, I'm choosing this to be, I'm measuring my distance from that point, not from 0, 0. Yep, because the whole action is to try to get a point here. No problem. Exactly. Right, and then phi minus 1 to whatever power you have. And then that will give you the value of the board. So initially, every square below the line has a chip. And so we want to know what is the initial value of the board. Exactly. And so this one is x to the 4th. This is going to be x to the 5th over here, then x to the 6th, x to the 7th, and then the other side, x to the 6th, x to the 7th. So if I want to calculate what is the value of the 0th row, it's x to the 5th plus twice the sum from 6 to infinity. Well, the sum from 6 to infinity, just pull out an x to the 6th, and it's a geometric series. It's a 1 over 1 minus x. The algebra is not too bad. You get 1 plus x times x to the 5th over 1 minus x. Each row is x times the row above. So if I want to sum all the other rows, I'm now going to have my value of the 0th row times x to the n, where n goes from 0 to infinity. Oh, that's another geometric series. It just gives me another 1 minus x. So I get 1 plus x, x to the 5th over 1 minus x squared. So that's going to be the initial value of the board. Now we have two types of moves. I have a piece jump over another piece. I can do it either vertically or horizontally. And one of two things happens. I'm always going to lose a piece. And the piece that's doing the jumping, it either ends up closer to the target or the same distance or further away from the target. Well, if it ends up the same distance or further away from the target as when you started, then you can't increase the value of the board. You lost a piece and the other piece has the same value as before or smaller. So the only thing I have to worry about is what if we do a jump and the piece is now closer to the target? Maybe that increases the value of the board. That's the only thing we need to look at. So let's assume we have a piece at x to the 6th and x to the 5th. And we'll assume, we jump over it. And so I'm just writing things off to the side so it's easier to see. So we jump the x to the 6th over the x to the 5th and it lands on x to the 4th. So we started off with things at x to the 5th and x to the 6th. We end with something at x to the 4th. And we can look at what's the value of the new configuration minus the value of the initial configuration. So we have x to the 4th minus x to the 5th minus x to the 6th. Pull out the x to the 4th. It's 1 minus x squared. If we choose x carefully, this is going to be 0, which means the value won't increase. And so more generally, if I have pieces at x to the n plus 2 and x to the n plus 1, and I land at x to the n, I have a very similar thing. I just pull out x to the n, and again, it's 1 minus x squared. So what are the roots of 1 minus x squared? Well, this is a quadratic. We can use the quadratic formula, and we get it's -1 plus or minus root 5 over 2, or it's just phi minus 1, or 1 over phi. It's just related to the golden mean. So if I choose that to be my value of x, then whenever I do moves, the value of the board either stays the same or gets smaller. So we could also choose an x that would make this negative. Yes. The golden mean is the cutoff. It's the critical threshold where things can happen. And so now, if I look at the initial value of the board, if I put in x equals, the golden mean minus 1, I get 3 minus root 5, which we all know is approximately 0.763932. And if I look at what would happen if I had a checker at 0, 4, well, if I have a checker at 0, 4, that would contribute just x, because it's 1 unit away from the target at 0, 5. That's going to be 0.618. 0.618 is less than 0.7639. So that means it is possible that you might be able to get a checker all the way up to 4. This doesn't mean you can do it. It just means it's possible. It turns out it can be done. It's a nice exercise. Try to show how to do it. If you are a visual person and you actually need hands-on, let me know. We have some department funds. I will see if we can buy an infinite checkerboard. But if you put a piece at 0, 5, well, we made things very simple. We assigned a value of 1, to that square. So the value of the board has to be at least 1. It'll be larger than 1 if we have a checker anywhere else, but it's got to be at least 1. And so if it's at least 1, can't be done. So this is a beautiful proof that you cannot get a checker as high as 5. We're not looking at any possible paths. We're not trying to prove anything clever. This is a high-level proof that it cannot be done. So what I want to do now is I want to just quickly ask you, we've got about a minute left, how might you generalize Conway's game? So I will be running a small group again this summer. And one of the things I always want my students to do is get in the habit of when you read a paper, ask, well, what can I do now? What other questions can we ask? So building on Conway's game, how could you change it? What else could you do? So you could do cubes. So that's great, is to go straight up to 3 dimensions. What if we had a 3-dimensional version of Conway's game? How far could we push things? What else could we do? So you could allow 1 by 2 things. Strange configurations. Hexagons. What if you change, instead of, you can view the rectangle checkerboard that we're looking at as a square lattice. What if you did things on a hexagonal lattice? You could also change the legal move. Maybe you have to jump over 2 pieces.
That leads to the question here is where do we do fraction?
Right.
And I don't see the complete fraction either. There must be something up, over, up, over, up, over. I'm guessing.
I have no idea.
Right. So then you're like, you would generalize it to 2 over 1 up, 2 over 1 up, something like that.
Almost like a night move.
Yeah. You might be
Right. And so I deliberately try not to think about what the answers might be. No, that's okay. Yeah, so here's just a bunch of things. The other thing is, if you've ever taken a class in abstract algebra, you talk about Ogawa theory, you eventually talk about what can you solve explicitly in terms of polynomials. When can you find the roots? You can do it for quadratic, cubic, quartic, but there's no solution in terms of just the coefficients. Or same thing when you do geometry. What constructions can you do with a straight and compass? Well, what if I start allowing some strange types of moves? What could we do in situations like that? So the goal is to just get in a habit whenever you hear a math talk, whenever you see a paper, whenever you read a theorem, is to just start asking, what can you do next? So there's not time in 30 minutes to go into detail about how this applies to Fibonacci numbers and some of the stuff my students have looked at, but it turns out you can create a game using the Fibonacci numbers. And it turns out that you can prove that as long as you don't start off with 2 tokens, player 2 always has a winning strategy, but it's a non-constructive proof. So you can get some very interesting stuff there. So thank you very much.